Hi, I'm Cecilia Zhang, a PhD student from UC Berkeley. I'm interested in helping people shoot casual videos that look great, like the ones seen in the cinema. A big part of the cinema look is the focus, and this talk is about autofocus for casual videography. Cinematic focus is appealing but challenging. What do I mean by cinematic focus? I mean focus is characterized by beautiful shallow depth of field from large lenses that visually isolates the subject and creates bokables of defocus the color. Cinematic focus also helps tell the story by guiding the viewer's gaze. For example, in this clip from 24, the focus pulls from the special agent to where he's looking, the couple on the staircase. But cinema focus is expensive to produce. On a movie set, the assistant cameraman marks exactly where actors must stand, and the camera operator controls focus in real time to track the action according to the screenplay. It takes a whole crew. But there is no crew and no screenplay in casual videography. Casual videos rely on autofocus in consumer cameras and is very error-prone. For example, in this clip with a DSLR camera, the autofocus starts on the baby, refocuses the wave, and here it should refocus back to the baby, but it's kind of slow. Of course, this is because the camera autofocus must work in real time and can only guess where the action will go. Now, most people shoot video on smartphones today. Here, the autofocus errors are less visible because the camera is so small that we cannot get shallow depth of field like in cinema. In this paper, our goal is to deliver cinema-like focus for casual videos. Let's look at an example to see how this works. Our system takes smartphone video as input. This input clip shows kids riding bikes. But the unexpected thing is that Mom is going to ride that tiny bike too. Well, if you were a cinematographer, you would tell your crew to first focus from one child to the next and then pull the focus to the mom when she starts to bike down the hill. Our system is able to create a very similar output. First, we synthesize shallow depth of field to isolate focus on one child and then the next. And now we pull focus down to mom to make her the center of attention as she bikes down the hill. This would be impossible with conventional autofocus, and it's possible in our system because it looks ahead to see where the action will go and preemptively moves the focus to follow the action. The main contributions in this talk are: we identify that good video autofocus needs information about the future. We make that future information available to video autofocus algorithms for the first time. We built a prototype system to demonstrate the potential of this approach. To do this, we first commit to synthesizing refocusable video. The first half of our system, called RVR, makes smartphone videos refocusable by synthesizing shallow depth of field at each frame. Second, we introduce look-ahead autofocus, or LAF. This is a new class of autofocus algorithms that looks at future frames in order to autofocus the current video frame. Of course, this is only possible because we assume refocusable video in RVR. Now let's see how we achieve this. I will start with RVR, how we synthetically create shallow depth of field video. The input to RVR is a casual deep depth of field video. Output is a refocusable video. What we mean by refocusable video, here is an example input deep depth of field video. And here is what's generated from RVR. In this scene, we are able to pause the video at any frame and refocus anywhere, from the shovel in the foreground to the kids in the midground to the family in the water in the distance. Synthesizing shallow depth of field is not new. Many smartphones do it for still photos, but not videos. Some of the technical approaches have been described in recent papers from Google, amongst others. The first research paper for videos was presented at CVPR a couple weeks ago by Jingqi Li and colleagues at Google. Their work is concurrent to our own and can be an alternative for our RVR system, but it did not address the full problem of video autofocus. Again, that requires look-ahead autofocus algorithms that I will discuss later. But first, let me discuss RVR. Our approach to making video refocusable is to extend CNN-based synthetic depth of field from still photography to videos. Here, I'm going to highlight 3 of the main technical contributions: our training dataset, HDR recovery, and temporal coherence. Let's go into detail for each. We built on top of the aperture supervision work proposed by Srinivasan and colleagues that first proposed using aperture dataset to learn depth from monocular VOs. We extended that work to collect not just pairs of photos at different apertures, but triplets where the aperture size and focus planes vary. We show in this paper that it gives much better depth estimates at large distances. We're making this dataset public for the research community. We trained the CNN to jointly predict scene depth and recover high dynamic range, then render a shallow depth of field image. We supervised training by comparing this rendered image against the ground truth photos with that depth of field. This is very practical because no HDR and no depth cameras are needed. We just shoot regular photos with different aperture sizes and focus depth. HDR recovery is key to render visually salient bokeh balls that appear at saturated region. Pro Tools' earlier work didn't recover HDR. We added this feature to enable rendering more photorealistic defocus blur. We observed that HDR recovery can also be indirectly supervised using aperture supervision. The idea is pixels that are saturated in the deep depth of field image are often not saturated in this shallow depth of field pair, because their energy is spread over many pixels. This provides indirect signal for the network to learn HDR recovery. Here we show an input video with deep depth of field. And here are renderings without and with our HDR recovery. Notice in the top that the background is erroneously flat, but with HDR recovery in the bottom, the rendering shows clear bokeh balls of defocused light. Finally, let me highlight the importance of temporal consistency. We used an off-the-shelf optical flow network, the FlowNet 2.0, to compute backward and forward optical flow between adjacent frames, and used these bidirectional flows to compute an occlusion map, which are then used to compute the weights for the temporal filter. Here is an input video in deep depth of field, and a comparison rendering with and without temporal consistency. The flickering artifact is alleviated with temporal consistency on the right. Let's look at a few more examples where our RVR system makes casual videos more visually appealing with shallow depth of field. Here we scraped some casual GoPro videos from YouTube. But we're not done. Let's revisit the Where is Mama video. The question remains, when and where should we focus each frame? What happens if we just apply shallow depth of field to it? It would make no sense because we will focus on the little child in the foreground and leave the most interesting thing in this video out of focus, which is the mom on the bike. This leads us to the second half of our system. Look ahead autofocus. This is a new class of autofocus algorithms that looks at future frames to decide where to focus. Remember, the core limitation of conventional video autofocus is that this is impossible. That's why we worked hard to implement RVR to make video refocusable at the first place. These are the three key concepts we introduced to organize and simplify how we implement our various lab prototypes. We define a new focus target to be the focus subject to focus on in the next frame, shifted from the previous focus target. In this example, it's from the kid to the mom. Once a new focus target is identified, shown as a blue diamond here, we use a vision-based tracker to track this new focus target backwards a few frames, to insert a focus pull from the previous subject to the new one, to shift the viewer's gaze just before the action happens. Then, we track the new focus target until the next new focus target is identified. Here is a slow-mo version of the focus transition in this example, where the focus gradually shifts from the previous focus, the kid, to the new focus target, the mom, right before the mom bikes down the hill. This pipeline illustrates what I just described to generate video with autofocus. This organization to lab reduces the problem to detecting new focus targets. In the paper, we explored different ways to do this. First, we built a GUI tool to allow the user to choose when and where to focus. This is efficient because instead of clicking focus at each frame, the user only annotates a few frames where new focus targets appear, and our tracker will track the selected focus target and the rest of the system is automated. In this video, the mango tart was the original focus, and the user wants to focus on the person when she's in the frame. The user simply selects her as a new focus target. The rendered video reflects how the user wants the focus to appear for this video, focusing from mango to the person, and then back to the mango, and back to the person, locking the focus onto the person by stably tracking it. The next step we took is to build scene-specific autofocus. Here we leveraged recent computer vision advances to computationally comprehend aspects of the scene that let us reduce all the new focus targets. Let's start with an example, a conversational scene.
Maybe it has 8 legs, though.
If it has 8 legs, it's probably a spider, and I don't want to come see it.
Ah, okay.
What we want is the video where the focus follows the conversation, magically pulling to the next speaker a moment before he or she begins speaking. In order to identify the new focus targets, we compute a heat map using an audio localizer. This is a recent breakthrough in computer vision that localizes where in the video audio is coming from. In this case, who is speaking. How it's achieved is very interesting. Andrew Owens and the colleagues at Berkeley detach audio source from a video and train a neural network to align the audio back to the video.
It has 8 legs, though.
If it has 8 legs, it's probably a spider, and I don't want to come see it.
Ah, okay. I guess that makes sense. It doesn't look very friendly.
We use discontinuities in this audio localization to identify new focus targets, essentially when someone begins speaking. The result is video that automatically pulls focus onto the next speaker before they begin speaking.
8 legs, though.
If it has 8 legs, it's probably a spider, and I don't want to come see it.
Ah, okay. I guess that makes sense. It doesn't look very friendly.
Let's maybe step back and imagine, what if we don't do look ahead autofocus, and just apply shadow depth of field to this conversation video? The focus would be contextually wrong, as we cannot see the person who's talking.
It has 8 legs, though.
If it has 8 legs, it's probably a spider.
We demonstrate scene-specific laugh on 2 types of videos, conversation and action videos where focus pulls frequently take place. Let's look at a couple of more results. There are some unexpected and memorable moments that can be focused using RVR laugh, like when mom kisses her child in the background. Or in this funny video, the focus pulls from the foreground bush to the back, apparently to something more interesting, following this child climbing up the hill right before he slides down. and his toy tumbles after him. Here's another interesting video result using audio-aware RVR laugh. It involves an interaction between a musician and a baby. The focus shifts from the child here to the guitarist at his expressive peak, and then transitions back to the child. Here are some more results that highlight how contextually aware look-ahead autofocus is needed to create focus that is meaningful. You are going to see pairs of clips. The first without laugh, where the focus isn't right, following by look-ahead autofocus to make it meaningful.
Apparently there's like, apparently this kid likes to interrupt. Apparently there's like, apparently this kid likes to interrupt videos.
Where are we? In Berkeley. Where are we? In Berkeley. Okay. Hang on, what do we got here?
We got bird nesters.
Hang on, what do we got here?
We got bird nesters.
More results can be found in the project webpage. So far, we showed that applying cinematic focusing makes casual videos look more appealing and interesting, and have demonstrated a research prototype being able to create such contextually meaningful focusing for casually shot videos. We believe that many components can be optimized and polished. Take a few spots, for example. In the RVR part, as we briefly mentioned earlier, Zhengqi Li and colleagues proposed to use mannequin challenge videos on YouTube to obtain high quality depth and trains a machine learning model to predict depth from videos. Advances in active depth sensing, dual pixel, stereo cameras, and high dynamic range capturing would benefit high quality defocus rendering. All can be used to synthesize refocusable video, but all would still need look-ahead autofocus. In the laugh part, we showed you specific scene cases such as conversation and actions. As we move forward, we want to have a fully automated new focus target detector that works for generic video contents. We made a first attempt at training a machine learning model to predict new focus targets given a video clip. To enable such training, we built a dataset of video clips with new focus targets annotated using our GUI, and train a neural network to predict the focus region and the probability of a query frame being a new focus target. Let's see what the learned model does. Let's see what the learned model does. In this example, given the input video, the model is able to localize the picked up dumpling as a new focus target and sets focus to it. Our system then tracks it. Similarly, in this scene, the model identifies the running child and renders the video with a focus pull right before the child runs into the frame. This is one way to formulate the problem using machine learning, but not the only way. As a starting point of this direction, it can be combined with many existing topics. For example, video summarization that automatically produces short summaries from long videos, video saliency detector to localize interesting image regions, a new video saliency dataset with attention shifts acquired using the eye tracker. Computer vision is moving really fast, and we believe that contextually sensitive, fully automatic laugh is possible. This means a full solution to the age-old problem of video autofocus is now within sight. By using image-based and physically-based rendering, machine learning combined with advances in scene understanding, we are able to automate certain portions of cinematic focus creation seen in filmmaking. We hope that this work attracts more research into video autofocus and envision that the research community can continue building upon it to make it a comprehensive solution. Finally, I thank my collaborators who altogether made this work possible. Thank you.